Okay, everybody, let's get started. Today we are going to finish lecture number 3 and starting with lecture number 4. Lecture number 3 is on threads, and it's on processes. Lecture number 4 is on threads. So today we'll really see the concept of threads and processes being brought together, hopefully in some sort of an abstraction that makes it clear in terms of what we're looking at. For those of you who weren't here last time, what we started with was this lecture. It's always weird when I start in the middle of a lecture, so I want to review the concept a little bit in terms of what it is we're talking about, and then start fresh where I left off. I was talking about processes in terms of what's happening, and that's really the abstraction the user has on the computer. When you're running your operating system, you're seeing everything in the form of a process, is what I mentioned before. And every program that you're running is running in the form of a process. So we have this concept of the scheduling of these running programs, and we have the cooperation between the running programs, and the communication that might go on. And then we have the looking at the different platforms for how processes work, and that's where we get client server and distributed computing. Because if you think about it, if you can take processes and distribute them over many different computers, then we've really established what's called a distributed computing environment. And if we have some processes that run on a server and some processes that run on a client, and we have them communicating back and forth, we have a client server. So a lot of the networking technologies and a lot of the concepts associated with networking are all process-based, which is kind of interesting. And when you talk about processes, you're really talking about operating systems concepts as a core. So that's why I like to spend a lot of time on processes in this class, because it really is a basis for what we're doing. We're creating a process abstraction when we create the user interface, where we have multiple versions of different processes running. We might have, in fact, on my computer right now, I've got a preview running. That's a process. I might have an email program running in the background. That's another process, et cetera, and so forth. So I talked about what process was, and I mentioned that it's a memory abstraction. And here's what it kind of looks like. And we have multiple parts of a process. The reason why I'm reviewing this is I'm giving you some hints in terms of what you want to see on the final exam and what you'll see on the take-home midterm. And so kind of the learning objective here. You want to know what a process is, and by definition it's a running program. So any program that's running in memory is a process. There's many different definitions of it. The book calls it jobs and processes. A job is a process, per se. We'll talk about threads later on today, and you'll see how that differs from a process as well. The process in memory is nothing more than an abstraction of memory. So we have the memory that's broken out into different parts. We have a stack, we have a queue. We don't have a queue. We have a stack, we have a heap. That's what I meant to say. We have data, we have text. So we can keep track of the running information of the process. What we don't want to do is keep reading and writing to a hard disk. Instead, we want to load all this stuff. The process is really that executable, that exe file loaded up into memory. When we double click on that file, we load it up into memory. It looks like this in memory. And so down here is the data and the text. Well, the text is pretty much the running instructions, and then it gets loaded on the stack. And then the stack might create some dynamically allocated memory on the heap. And we're using this process space to run the process, essentially, and to organize what's going on with it. When the process is done running, it goes out of memory. So this stops, and it terminates at the end. So it's kind of interesting in terms of the abstraction. And this is also sometimes referred to as the runtime environment. So the runtime environment is the process stored in memory and the running of the filling up the stack, emptying out the stack, filling up the heap, removing items from the heap, and going back and forth. And that works with CPU scheduling, as I mentioned last week, and a couple of other concepts as well. So the processes have many different states associated with their lifetime. When a process starts up, it is new. It just starts, and it's not really running, it's just new. When it actually has some instructions executed, then it turns into the running state. And then it could be waiting at any one moment of time, so the process is waiting for some event to occur. It may also, when it's not waiting, it might be ready. Instead of going back into a new state, it pretty much goes from new to ready again. And ready says that it's waiting it's waiting to be assigned to a process, or it's waiting to have something happen to it. And then it could be terminated at any point. So, and then we have Unix system calls that create processes and kill processes. In fact, to terminate a process, you just type in kill. To start a process, it's usually in the form of a thread. So it's a P thread or a thread, depending upon what library you're using. And then you go ahead and start a process. So that first assignment is really on this concept, the one that you're doing the shell for. So, and I know a lot of you guys are working on it, which is fantastic, because you don't want to wait till the very last week of the class to turn everything in. And it's better to do it earlier, actually, especially because this is the summertime. The last week of class, you'll be enjoying the last couple weeks of summer. You don't want to be like doing this stuff. Plus, the first assignment is also the hardest. So when you get past the first one, the rest of it's a piece of cake, actually. So some people will probably just wait till last to do the first assignment, but it's okay. All right, so here is the running process and a diagram of the process state. So we have new, and then it gets admitted into a ready queue. The ready queue comes back and says, well, from the ready queue. And think of these as queues if you want to. We have a whole new queue, we have a ready queue, a running queue, a waiting queue. In fact, when we start looking at CPU scheduling, which is probably not going to be till next week or the following week, you'll see how the queue abstraction is used for the processes, and processes just spend most of their life in different queues, waiting to get stuff done. And then usually the big old question comes into play, says, well, why so many queues? Why do we have to do this to it? Because we want multiple processes to run simultaneously. So in a multiple threaded, multiple process system, we have to set up some elaborate scheme to get all this stuff to work simultaneously. Otherwise, we just have batch processing, where one process runs, it stops. One process runs, it stops. One runs, it stops. So it doesn't give us the same user experience. Is there anything wrong with that? No, in fact, that runs faster. It runs much faster than having to do all this stuff, because what we really want to do is just run the process, right? So that's why more processor power and more processors on the system, it makes your system run faster. Think about it. So all the information about the processes are stored in what's called a process control block. A process control block is held by the kernel and the kernel memory, because remember from lecture 1 we have user mode, kernel mode. Kernel mode has the memories associated with it. And again, this is another abstraction. User mode is memory spaces above a certain level. Kernel is just memory below a certain level. When you start up, we don't want to keep reading and writing to a disk. Instead, we just load everything up into memory, and then we read and write from the memory, which is kind of interesting. In fact, of all of operating systems concepts, I think memory management is the most interesting in terms of how in the world did someone invent this scheme of doing stuff this way. So process control block held by the kernel stores the information about each one of the processes. It might hold the state, the program counter, what instructions did it leave off, which is the next instruction, the CPU register, CPU scheduling information, and memory management information, accounting, I/O status, and stuff like that. So again, it's another piece of memory that's being held for each one of the processes. So here's a kind of an example. If you were to actually see a process control block, it would sort of look like that, kind of, sort of. None of this stuff really has pictures to it. They're all concepts. I also talked about and introduced the concept of CPU scheduling last week, and CPU scheduling switches from one process to another, and here we have two processes running, process 0 and process 1, and then we go back and forth by saving states, reloading states, saving a state, reloading a state, in order to achieve that multi-programming that we're interested in seeing. So, now this is going to be slow compared to just running one process, running a second one, running a third one, sequential processing. But unless you want to go back to the DOS days, Windows is going to require something a little bit more elaborate. Back to most of your desktop experiences are facilitated by multiple processes running in a pseudo-simultaneous kind of form. So process scheduling has different queues associated with it. As I mentioned before, scheduling is all about those queues. Process is all about living in queues. So we have the job queue as an example, which is a set of all processes in the system. They call them jobs because you're going to call it a process queue? Well, they're all process queues. So this is going to be the job queue. And then we have the ready queue, which is all the ones that are ready to run. And they're in memory, they're waiting, they just need to run. And we have device queues. So we separate out the CPU processing from the device processing. Then we can, kind of intelligently schedule things a little bit more efficiently. If everything were waiting in the same queue, we would be waiting a very long time for the CPU or a very long time for the I/O. Bottom line, I/O takes longer. So if you're having a process come into the queue, you're going to separate it out, put it into a device queue. Say this is waiting for the CD-ROM drive, this is waiting for the disk, this is waiting for something else. Because if it sits there waiting for the CPU, which everybody has to have CPU time in order to run anyway, then you've got a big, long, huge CPU queue. So then they have this concept of short-term and long-term and medium-term queues, where this kind of fits into place. So we're going to have a job queue, we're going to have a ready queue. Now these device queues, they can be separated out into different lengths, and that slide's not coming up for a few more, but if we have short term, those are CPU bound processes. They're getting in short bursts of a CPU. They don't need too much of the CPU time. If we've got a long term, they're waiting for I/O essentially. They're waiting for the I/O device to become available. And as I mentioned last week as well, it's not only the time that the process is waiting in the queue, but the nature and how many bursts is it getting. So we measure quantums or bursts is the measurement associated with time. This time is associated with how much time are we going to allocate for this process to use this device, this process to use the CPU, etc. and so forth. So you'll see a bunch of different terminology used. I like to use bursts, CPU bursts, instead of quantums. Quantums, 2 quantums, 3 quantums. Some people use the two terms intermixed as the same thing. There really are supposed to be 2 separate terms, and they do mean 2 separate things, and I'll get to that when we start talking about CPU scheduling. So here's an example of the ready queue and various different I/O device queues. The ready queue has here's a ready queue here, has a head and a tail. And for those people who are familiar with linked lists, you might wonder, well, isn't that kind of like a linked list? Isn't it? Yeah, it is very similar to a linked list. A lot of the queues themselves are going to be stored in a linked list. It's easier for putting something in, moving something around. It's a rotating circular queue. So in terms of the abstraction, it lends itself, and we're working with memory. So why not have that memory just point to another memory, point to another memory, point to another memory. So we have a head and a tail in this queue, a head and a tail, a head and a tail. And this might be for different queues for different purposes. That says mag for mag tape, so disk, terminal. I don't think we have any mag tapes anymore, but kind of brings back memories like tape drives. So we have CD-ROMs now, and big old SD cards now, no tape drives. So tape drives have their place in time though. And you may also notice here we have multiple PCBs, process control blocks. This is a multiple PCB configuration. Usually somebody in the beginning kind of wonders about it and says, well, how many of these do we have? You can actually have as many PCBs as the configuration as what would make sense. For example, you can have a process control block for all processes, and then inside the process control block you can have a sub PCB and then another sub PCB inside of that. So if you can layer them or nest them together, then you can really keep track of everything. What you don't want to do is have, like the old days, have a single PCB that runs everything, because then the queue gets kind of big, and if the queue's big, you got it, the sorting and the searching through it takes a longer time, bigger search space. So if you can pinpoint what you're looking for, exactly where you're looking for it, and only have a couple of items to kind of scroll through, process is much faster. So when you study operating systems and you start building your own operating system, that's when you start taking advantage of your algorithms and data structures classes, because then you can build heaps and you can build trees, so you know the data structures and then the algorithms for which kind of sort's going to work for efficiency purposes, and what kind of search are you going to try and do, and how you're going to optimize the data structure to work with the search a little bit more efficiently. And so that's when it comes together essentially. Here's the presentation of the process scheduling. So we have a ready queue up here. In the ready queue, everybody goes to the CPU, and then we come back down and we go into, maybe we have an I/O request, or maybe we have a fork a child, or maybe we're going to wait for an interrupt, and then we're going to come back, and the interrupt's actually going to occur, then we're going to come back up, and we're going to be in the ready queue again. So processes do a lot of waiting, actually. They do a lot of sitting around and waiting for stuff. The wait time of a CPU scheduler determines its efficiency. So when we're going to get to CPU scheduling, we have an assignment to do that is a simulation of a CPU scheduler, and you'll start seeing how the pieces will come in together. Depending upon what algorithm you choose for the scheduler, the wait times might vary. So it's kind of interesting how that works. And schedulers, here we go. We have the long term and the short term. Long term is everybody. It's the job scheduler. CPU is short term. It's only brought into memory for CPU time. And it selects each process and then allocates the CPU to the next one. So it works efficiently that way. We also have this concept of the addition of the medium term scheduler. Well, medium sits in between short and long, doesn't it? So we have partially swapped out stuff. We just put one in between as a kind of a catch-all for the parts that are in between. So if it's not in the short, it's not in the long, it might flop back and forth. It makes it so it's a shorter jump, especially if the short term is kind of time consuming. We can put some stuff in the medium, delay it, prioritize it, and then, because we have priority to think about as well. Most of your kernel level processes get higher level priority than your user mode processes, because if it weren't for the kernel, the user's not going to run. The user mode's not going to run correctly. So we need to make sure all the kernel level stuff gets run. So we talk about the schedulers. We have the short-term scheduler. It's invoked very frequently. It's in milliseconds. It has to be fast, because if we have a short-term scheduler that's slow, the entire computer is going to run slow. This is what gives us our user experience. This is what gives us how fast things run. It doesn't really matter how much memory we have on it. If we have a really bad scheduler, we have a really slow computer. So, long-term scheduler is invoked very infrequently. Might be slow. It's not going to get. Probably will end up with a longer time as well because it needs more resources. And the long-term scheduler controls the degree of multi-programming, which means how many processes can we have running simultaneously. So we can describe processes as being I/O bound and also CPU bound, as I mentioned before. So I/O bound is waiting for some I/O. Well, but you think about it in a nutshell, what do we use our computers for? Mostly I/O. We're mostly, moving a mouse, typing on a keyboard, accepting a command from somewhere, responding to interrupts and stuff like that, which is all input-output, when you think about it. So spends more time doing computations, very few long CPU bursts if we're an I/O-bound process versus a CPU-bound process. The CPU is going to spend more time with longer CPU bursts, less I/O time, and vice versa for the I/O. I also mentioned the concept of context switching in the last lecture, and context switching is nothing more than running one process, saving its state, updating the PCB, and then running another process. So we have one process running, then another process, and another process. Saving the state, loading one up, unloading in the other one, context switching. So the system does no useful work when switching. The higher level of context switching is the slower running computer. So the more context switching you're doing, the slower your computer's running. And I think I brought up an example last time with, just load up like 5 different versions of Microsoft Word. Or 12 different versions, and only use one of them. It'll run slower than if you have just one of them loaded. So, long story short, close down those programs you're not using. It's a higher level of context switching because the process is still out there. If the process is still out there, it's not going to get garbage collected because you're still using it. It still has an entry into the PCB. It's still running. So every once in a while, it's still got to check, are you still running? You say, okay, we're minimized. Okay, keep going, keep going. It's still checking. It's basically using CPU power, even though it's minimized, which is kind of ironic, actually. So it all starts with the process creation, and then so we have a parent process that creates a child process, and we have resource sharing. In most modern-day configurations, the parent and the child share the same memory address, and the child gets a copy of the parent's memory address, but they're all located at the same spot. Because they're all sub-processed and they're all in the same hierarchy, so they're all running together in the same memory location. But they could keep separate memory amongst themselves. So the child gets a copy, and then the child can change it around, and then in the end it goes back to the parent. In terms of the execution, the parent and the child execute concurrently. Usually one of them is running at a time. So the parent will wait for the child to terminate, then the parent will start running again. So in the process creation, we have the address space that is being used as the abstraction, and the child duplicate of the parent, and then the child has a program loaded into it, into the terms of the child. And then on the Unix examples, we have fork and exec. So this is really going back to that first assignment that I've been talking about. So the process creation, if we were to look at a diagram of it, so it kind of looks like this. Now, does it really look like this? I don't know. So this is somebody's abstraction of it. And when we use the fork, and this is a system call, by the way, we have a parent waits and the child runs. So this is what you're programming in that first assignment when you're creating the shell. So until you actually kind of work with it, it's hard to sort of see it work, which is why I put together an assignment for you on that. So here's the C program that forks a separate child process. If you're not familiar with C, then you're doing the alternative form of this and writing pseudocode, or you're putting a lot of notes in here to make up for what you don't understand in terms of the programming component. And the idea is not necessarily to get a perfectly running, compilable, running program in C, especially if your background's in healthcare or something and you're not a programmer. It's going to be impossible for you to write this. Learn an entire C language and program in threads all in one assignment. Not necessarily what I'm asking for. But if you are familiar with C, and if you are a computer science major or software engineering major, I highly recommend learning C. In fact, I think I'm teaching C. So I'm teaching C++ in a weekend course. So maybe some of you are in that class. Anyway, if you are familiar with C, we have integer main going on here in a main program. It's not object-oriented, it's procedural. We're going to fork. This is a process. When we run the program, it turns into a process, so our process is forking another process. So our running program is main, and our running program is the main process or the parent process. When we fork, we create another process. We're waiting while this forked process is actually running. And then we can check for an error, and if not, then we're going to run an exec in this particular case, and this is an LP, exec LP. When you write that program, you're going to see WP, LP, PP, you know, all these different switches. It's because this is a procedural, not an object-oriented program. We have different function calls for different versions of this. What are all those different versions telling you is how many arguments and what order are the arguments coming in. Because what we're doing is running exec, which just essentially says execute, short for execute. What does execute do? Well, in the child process, it's going to run a program. In this particular case, it's going to run ls. So this is actually, if you're going to write that program for assignment number 1, this is a good base, actually. Compile this, see if it runs, actually. So. And if you are going to do this, you want to install Linux or get a startup disk. I investigated the Amazon servers, and it's great. However, it's all cloud-based stuff, and there's no C in there. Not going to help you, actually. There's no GCC compiler on that you can use. It's actually more for web programming than anything else. So what I would highly recommend is doing a Google search, downloading one of these disks, ISO files for Red Hat or for Debian or any version of Linux. You burn the disk, the DVD or the CD, you stick it in the computer, you reboot the computer, it boots to the live disk. It's a live Linux disk, and it gives you a live Unix system on your computer. And then put in a USB drive. Everyone's got them nowadays, a little thumb drive. Save your work to the USB drive. So you can even write it in Windows as an example using Notepad. Save it to the USB, mount the USB inside of the Linux thing and see if it runs. Compile and run it. Whether it compiles and runs doesn't really matter to me. It's the source code I'm looking at. So here's a tree of processes on a typical Unix Solaris system where we have an ordering to this. Now this is going to be different for each version of Unix and each version of Linux. So it'll be interesting to actually see what is real, but usually it's in the triple digits, not the quadruple digits, not the triple digits, because the processes, there's a lot of processes at any one moment in time. The kernel's got more processes, but it usually starts the user mode after 0 and 1, so 0, 1, 2, 3. And then we have some starting level for the user mode at that point. So process termination, if you are a C programmer, you probably have used the word exit maybe before, exit 0, exit 1. It's kind of like return, but return takes you back from a function. Exit kills the process and within inside of the process. We can also perform a wait, and that works too. What does that do? Or a sleep 5. Process just sleeps for 5 milliseconds. Or wait. If you do wait, you'll hose the process right there. until it wakes up. Also, a parent may terminate the execution of a child, abort the child, essentially. And then the task assigned to the child is no longer required, it goes away. We have cascading terminations that exist, where a child terminates and then the parent terminates and then the parent of the child of the parent terminates. So it cascades all the way back up to the one who created it. Why do we do that? Because we can actually terminate a child without terminating a parent, or terminating a parent without terminating a child. And we can only get to these processes by their hierarchy. So if we're a parent and we create a child and then the parent goes away, we've created an orphan child process, and there's no way of controlling that process. It's out of control. There's no way of terminating it, no way of stopping it without rebooting the computer, essentially. We have processes like daemons that don't have a parent, that are out there to do print jobs and all sorts of things. So, orphan processes are not a bad thing when they're done on purpose. It's kind of like the state machine as the endless loop. Not a bad thing when it's done on purpose. You can control it, kind of thing. So, in terms of processes, the other thing I mentioned, and I'm still reviewing from last week actually, I covered a lot last week it seems, cooperating processes. Sometimes when you hear it multiple times though, it kind of makes more sense. So we have independent and then we have cooperating processes. Now if we had independent processes on a system, we might as well just have batch processing, because everything is going to be running on an island of its own, and we can just do sequential. Oops, okay. We could just do sequential processing, one right after the other, and they would all be independent, but that's senseless. So when we have cooperating processes, we have processes that can be affected or be affected by the execution of other processes, and they're all working together. So if we separate things out, independent, nothing can affect anybody. It's all independent, island of their own. Cooperating, they're all working together. The advantages of the cooperating processes over the independent is we have information sharing, and then we have computational speed up and modularity and convenience. So if we're saying that everything on the computer is running in the form of a process, and we have 5 processes and they're associated with 5 programs and they're equally scheduled, each program is going to run at the same speed. If we take one of them and add more processes to it and put them into the batch, that one program is going to run faster. So it speeds up the execution of the program itself, the more processes that are associated with it. So we have threading that comes with this, and we can create this abstraction through threading, multiple threaded threads that are all associated with one process. And so then we can create a pretty interesting scenario where we have one program that's going to run faster than the other programs, if we can work it out this way. Most modern day operating systems don't work that way. Everybody runs at the same speed. So all user level processes are going to run at the same speed as as each other, and then we have kernel level processes that are going to run faster. So anything that's associated with the operating system is always going to run faster, but it's always going to run at the same speed. So producer and consumer problem, which is one of the scenarios that leads to process communication. So we have what's called IPC, inter-process communication, and then we have different classic scenarios that are associated with running processes. Producer and consumer is one of the classic ones, where we have 2 processes cooperating with each other, a producer that produces something and then a consumer that reads something, that processes something. Think of a CP command. We're going to read a file, put it into memory, take the memory and write it out to a file. If we can do that, then what we can do is have one process. Are we ready? Yep. Okay, so let me pause this for a second. Alright, so let's pick up where I left off. So I was talking about producer and consumer problems. So in this particular case, we have 2 running processes. One's producing, the other one's consuming. In that particular scenario, we're looking at something similar to, like, say, a CP command or a copy command, where we have one process that's copying a bunch of information into memory, and then we have another process that's reading that same information out of memory, but one's not waiting for the other. So they're mixing back and forth, and they're running faster than if we were to take everything, copy it all up, and then everything, pull it all down. So with two running cooperating processes, what ends up happening is we get faster processing, bottom line. However, you have to be able to make the processes communicate with each other and then do it correctly. So you don't have scenarios in which one process is constantly overriding another process and they're not talking to each other correctly. So we have different models that are associated with this. Most of them are memory oriented. So we have unbounded and bounded buffers. The buffer is the information that's being stored between the two processes. In an unbounded buffer, we're placing no particular limit on the size of the buffer. On a bounded one, we're setting a limit. We're setting a size on it. And I also showed you last time some information regarding the bounded and the unbounded, the shared memory. I'm going to skip through the source code examples, assuming that not everybody in here has a programming background, and it's not really going to make very much sense to you. Instead, flipping through to inter-process communication, which is what IPC stands for. So that's the mechanism for processes to communicate and to synchronize their actions back and forth. So we have a message system where the processes communicate with each other without resorting to shared variables. And then we have the IPC that is done in terms of sending and receiving in that particular model where we've got a message and we send a message to some process, receive a message from a process, and vice versa. So it's message exchange, message passing. We also have a shared memory where we have memory that could be seen by both processes, or a mailbox approach actually as well. So P and Q wishes to communicate. They need to establish a link between the two of them and exchange messages back and forth. So implementation of the communication link could be physical or could be logical. If we're going to do a logical, using logical processes or physical, it depends on what kind of memory we're using, how we're going to establish the memory communication, and then whether or not we're going to have kernel level support for it. So some implementation questions usually come into place in terms of how we're going to design this. How are the links going to be established? So this is why some operating systems like Linux and Unix, as an example, that support from a kernel perspective, it supports the inter-process communication. So we have the messages to send and receive, and we have different system calls that are implemented to help processes communicate, versus operating systems like Windows and Windows, that's a good example, that don't have kernel level support for this. So in a Windows environment, as you notice, you can't program with threads or processes from a user perspective. It's because the kernel doesn't support it from user mode. So, which is kind of interesting. So naturally it's not going to support inter-process communication either if it doesn't support the creation of threads or processes. So it can be linked associated with one. Are you going to link more than one process together, or is it two or more processes in terms of the link? So Unix actually provides multiple process linkage. So it's more than just two. Yeah, well, you have to have two cooperating processes in order to have an inter-process communication. Whether you're going to have 3 or 4 or 5, well, you can actually have a lot in a Unix system. How many links will there be? Just one link, or will there be a send link and a receive link? What's the capacity of the link? What's going to be used for? Size of the messages? Whether messages are going to flow in both directions. Can one process just talk to another process, or is it both of them talking back and forth that are going to facilitate this? And then I actually, getting close to where I stopped last time, actually, I looked at communication models where we had process A and B, and then here we have the shared memory, and here we just have the message exchange going back and forth between the two processes. And the message exchange is really called direct communication versus the indirect. Indirect is using a mailbox or shared memory. Direct is really one process sending a message to another process. And processes have to be named so explicitly. So P, send P this message, receive from Q, receive a message from process Q, and here's the message, just to receive. So the linkage is very explicit, and then we have the communication link where we have that's established automatically. And link is associated with exactly one pair of communicating processes. So between each pair there exists exactly one link that goes back and forth. And the link may be unidirectional, but it's usually bidirectional, which means information should flow both directions. So In an indirect communication fashion, that's when we have a mailbox. So think of direct from a user perspective as instant messaging or text messaging. You're directly sending a message back and forth with a text message or with an IM. Indirect is more like email. You're, at one moment in time throughout the day, you're going to check your email. And you're not going to get the message instantly as soon as the person sends it to you. You're going to get it a couple hours later whenever you check your email, unless you happen to be on email constantly. So it's indirect. So the messages are directed and received through mailboxes. And they're also referred to as ports. So each port might have a buffer that's storing the messages that are being received and sent on it. Each mailbox has a unique ID associated with it, and the processes can communicate only if they share a mailbox. They have access to the mailbox. So how many are you going to have checking that mailbox? Well, in the email scenario, each user has their own mailbox, and everybody has a mailbox. There's no sharing of the mailboxes normally. But in a Unix environment where you have multiple running processes, well, you could all share a mailbox if you wanted to. In fact, sometimes you do, like support, technical support. One person or multiple people might be checking an email address for technical support. Hopefully multiple are, otherwise you got bad service going on. So, properties of the communication link. The link is established only if the processes share a common mailbox. And link may be associated with many different processes, and then each pair of the processes may share several different communication links, might be different mailboxes. And links can be directional or bidirectional, so unidirectional or bi. So operations that are associated with indirect communication could be creating a new mailbox, sending and receiving through the mailbox, destroying a mailbox. So primitives are to send a message, to receive a message. Send a message to mailbox A, receive a message from mailbox A. So I believe this is probably right around where we ended last time, actually. So indirect communication here. In terms of the mailbox sharing, we have process 1, 2, 3 that share mailbox A. And P sends 1, 2, and 3 receive. Who gets the message? Interesting scenario. If it doesn't really matter who, one of the processes that have it might get it. It's kind of like how someone leaves a post-it note and then multiple people read it, but who really read it, or who's seen it, who hasn't seen it? Probably one of the most confusing parts of this form. So in terms of the solution, allow a link that's associated with at most 2 processes. So you're only sending it to one person instead of sending it to a group. And then only allow one process at a time to execute a received operation. And then allow the system to select arbitrarily the receiver. And the sender is notified who the receiver was. So let's talk about synchronization in terms of multiple processes. And I believe this is the new information for this week. But it kind of helps to go over, because we only meet once a week, it kind of helps to review sometimes. And this is an important lecture to review. So we have blocking and non-blocking. And this applies towards CPU scheduling, I/O scheduling, process synchronization, all 3 concepts. So throughout the next 3 or 4 chapters, we're going to hear blocking I/O, non-blocking I/O, blocking CPU, non-blocking CPU. When you're using the CPU for something, the process is going to block all other CPUs. Only one person can actually use a CD-ROM drive. I/O is normally blocking. Because if you interrupt I/O, you're going to spend more time interrupt, restart, stop, start, stop, and if you just let the job continue, because it's a slow process. CPU, however, doesn't necessarily have to block. So what's meant by blocking? Blocking is synchronous. Non-blocking is asynchronous. And then you're wondering, well, what's synchronous versus asynchronous? Synchronous is multiple things happening simultaneously. It's not one at a time. Asynchronous, it's one at a time. In an asynchronous operation, in a non-blocking, which is asynchronous, we have something happen, something else happens, something happens, something else happens. We don't necessarily know the timing of this, just one thing after the next. So message passing can be either blocking or non-blocking. Blocking is associated with synchronous. Blocking send has the sender block until the message is received. Blocking receive has the receiver block until it is available. The way you think about this is go with the walkie-talkie environment. We have 2 processes that are communicating. You guys are familiar with walkie-talkies. Or even in the old days, somebody in a blocking mode, if the speaker is speaking, the receiver is listening. They can't speak simultaneously. So even though it's synchronous, it's all happening one after the other in line. So it's like sequential synchronous. Hey, how are you? And the person comes back and says, I'm fine. And they go, okay. And then they press a button in the walkie-talkie mode. One can talk, the other one. The button is a blocking mechanism. So processes can do this to communicate with each other. Or in a non-blocking mode, non-blocking, the send has the sender send the message and then continue. You just say, hey, here's a message. It's like email. You send it out, you send it out, you send it out. And then you can continue and do other work. You're not sitting there waiting for the response. If you're sitting there waiting for a response back, you're doing it incorrectly. You shouldn't be sitting there waiting for a response back. That's asynchronous mode. And non-blocking in the receiver has the receiver. The receiver receives a valid message or it receives nothing. Null. Hey, you might want to check with the front desk. They just did attendance. If you want to get credit for being here, you might want to investigate that. So, buffering. So, the queue of a message attached to a link, limited to one of three ways. So, if we're going to buffer, which is the best way of actually keeping track of these messages, otherwise we're going to lose them. So, buffering is kind of like the voicemail, kind of spot to save the message at. Oh, this guy's going to have the same problem, but you know what? I'm not even going to bother. They'll get it in the next couple weeks. They figure out, how come I'm not in attendance? Zero capacity, zero messages. Bounded capacity, infinite length of end messages. The sender can wait until the link is full. Hey, there's plenty of room up here. I don't know why you're going to stick a chair in the back. Actually, there's a spot right over there in the corner, too. But you know what? You might want to check with the front desk because you just missed the attendance. All right. All right, so just know that the buffering can be of many different sizes, and it can be facilitated in many different ways, depending upon the need. So as I mentioned before, when we have inter-process communication, we set up the communication between the channels, and here we have the client-server communication. That can be set up. I'm not going to bother with this one either. So in a networking class, you usually talk about sockets. And then you have buffered information that's connected with the sockets. So in a socket, it's a Unix system call normally that creates a socket. It's bound to a port, IP address, and we send and receive back and forth through the socket. The socket's sort of like the mailbox in that scenario. And then we have this thing called remote procedure calls, or RPC, which is the original form of shared communication, where we have procedures that are called from one computer to another computer that are done through processes, where one process would signal to another process on another computer and say, hey, could you run or do this or do that? And then we have communication that exists between multiple computers or multiple sockets or multiple ports. And then along came RMI, remote method invocation, which is implemented in Java. All three of these forms use multiple processes to facilitate the communication, and the multiple processes are running from, in this particular case, multiple computers. So networking, in a nutshell, is nothing more than a bunch of processes communicating with each other from different computers. And they're using something to communicate, a port or a socket abstraction. So here's our socket abstraction, which is the primitive kind of form. So if they're not using a socket, they could be using what's called let's say an RMI manager or something, where we have a registry where we're keeping track of different computers and different RMI engines, and we basically are loading, it's kind of like a JVM, but it's a manager that's keeping track of the communication between the different computers. So if you take Java EE, you'll learn more about RMI in terms of a network, or take a networking course. You'll learn more about that particular concept. But it's hard to talk about operating systems without talking about networking, because operating systems are generally networked. So, sockets. That's the primitive at the beginning of time. We had, beginning of Unix, we had sockets. So a socket is defined as an endpoint of communication. and concatenation of the IP address on the port. So here's a socket example here. We still have sockets today. Every single computer's got a socket on it, and we all have ports. We may not necessarily be using all those ports, but we all have ports on our computers and we all have sockets. So communication consists between a pair of sockets that might be working. So here's an example of socket communication, and where we have host X, and then we have a web server over on the other side, and we have a socket here that is bound to an address, and we have a socket here that's bound to an address, and we're just sending information back and forth through inter-process communication, which is why I'm mentioning this at this point. In the remote procedure calls, the RPC model, we have a procedure call between processes on networked systems. We have this thing called a stub. So we have a client-side proxy, the actual procedure on the server, and then we have the client-side stub, locates the server, and then marshals the parameters. So then we have server-side stubs that receive a message. This does nothing more than the format for the messages and the abstraction of keeping track of the sending and the receiving, packing, unpacking, marshaling, performing operations and procedures on the server, back and forth. So here's an example of the execution of an RPC where we have messages that reside between the client and the server. So on one end we have the client, the other end we have the server, and then we have our message exchange that's going back and forth. So not a networking class, so I'm going to just go through a little bit briefly on these concepts. But here's the remote method invocation, RMI, which is the Java version of the client server and distributed processing essentially. And so they have the Java mechanism similar to RPC. RPC is the Unix first form of it, and then RMI came at second, so it's just the Java form of it. So we have a JVM on one, a JVM on the other, and we invoke different methods for different objects on each one of them. What does this do? It takes advantage of economies of scale. So we have many different clients connecting to a server. Well, they're not always creating their own instances of all these objects. They're sharing objects. And then they're invoking methods on objects that already exist on multiple computers. So it basically connects multiple computers together. So. Alright, I'm not going to get into marshalling. It goes way above and beyond the scope of this course, actually. Take a Java EE course, and then you'll get into that. So that was my spiel on processes. And then we have threads. Now, the author of this book puts threads and processes in two separate chapters. In most computer science, software engineering students taking operating systems for the first time are always confused. What's a thread? What's a process? Aren't they the same thing? Because some books actually call them the same thing, which really abstractly they are sort of, because they're very similar in concept. But as I mentioned before, threads are normally processes are normally a user level abstraction. Threads are normally a kernel level abstraction in terms of what we're working with. We have processes, and then we have what people call lightweight threads, so they can memorize the differences between the two of them and then go, well, multiple threads can be inside of one process. But isn't a thread a process? When you think about it, if you have one process and inside the process is only one thread, abstractly a thread is a process, back and forth. But if you want to remember it kind of in a generic fashion, process is always what we're running at a user level. Thread's always what we're running at a kernel level. Nowadays we have a one-to-one mapping. So if we have a one-to-one mapping, we could call that process a thread, we could call that thread a process. Isn't it the same thing in terms of its naming convention? So let's talk about mapping then. So we have multi-threaded models. We have threading issues, p-threads, Windows XP threads, Linux threads, and Java threads, and then multi-threads. So here's the concept of single and multi-threaded processes. Remember that thing I stopped at today, and it was a big old line, and I said it's memory. I said processes are memory abstraction, and inside the process we had the code, the stack, the heap, the text, and all that stuff. So we have the same thing. So we have single versus multi-threaded processes. Threads live inside of processes. So a thread is a thread of execution. A process is a running program on the computer, which is why I always say user mode, has running programs. Kernel doesn't normally run programs. Users run programs, but kernels run threads because we have to execute something. And the CPU scheduling is really process scheduling, but it's really thread scheduling. Think about it. So here we have one thread of execution inside of one single process. Here we have 3 threads inside of one process. Why do we want that? Well, if we were to take a process, break it out into smaller pieces and schedule it all together, we're going to get more processing done, which is kind of interesting. So if we can create multiple threads inside of one process, and then we have multiple, three things working for us instead of just one from a kernel perspective. So it makes things run faster. So people do multi-threaded to make their programs run faster. If the entire program is running in one thread, you're getting one single process abstraction, one thread that's running. If you have multiples in there, you're getting more CPU time because you own more threads. And the CPU's got more threads. Benefits to multiprocessing: responsiveness. It's a lot more responsive. The program itself is getting more power. It has 3 of them instead of 1. Resource sharing, economy, and utilization of MP architectures. Yeah. So you're utilizing the architecture a little bit more, especially if you look at different types of operating system designs for different types of hardware. Some of them want multiple threads because you'll get more processing done. And then economies of scale. So we got user threads and we got kernel threads. User thread is like a process. We have thread management done by the user level thread libraries. That's the P threads, or POSIX threads in Unix. 3 primary thread libraries. POSIX is the Unix. There is a Win32 thread and there's a Java thread, which is why I said you could do that first assignment in Java if you'd like. You can create a shell in Java. Shells, Java supports threads. This is kind of hard to do. The Win32 threads, there's no user level control on it. But you still have threads in in Windows. In Unix, you have POSIX threads, or P threads is what most people call them P threads. And you have user level control over it. So it's a little bit different. So you can create multi-threaded programs in Unix, but you can't do that in Windows. But Windows supports threads, but only from an operating system perspective. User mode can't create Windows 32 threads. So this was user perspective of threads. So user threads. Now we have kernel threads, supported by the kernel. Everybody's got kernel threads. Windows, Solaris, Linux, Unix, Mac, everybody's got threads. Why does everybody have kernel? Everybody has kernel threads. Because kernel is, we have a kernel on a Windows system the same as we have a kernel on a Mac or a kernel on a Unix box. And the thread is the form of processing that's being performed by the CPU. So it's all thread based. So we have multi-threaded models. And there's been a lot of experimentation with the multi-threaded models, and this is another source of confusion for a lot of computer science students when they go, what's this one-to-many, one-to-one, many-to-one kind of concept? So I'll kind of give you some examples of how this would work. In the many-to-one, which means there's many threads mapped inside of one process. So we have many user-level threads mapped in terms of a single kernel thread. So when we talk about the mapping, we're going user thread to kernel thread, or kernel thread to user thread. So one to many is one user, many to one is many users inside of one kernel. One to many is one user inside of many kernels. It's the opposite. So many kernel threads, user level threads mapped inside of kernel level threads. This is what we get with Solaris and GNU portable threads. So when you're actually creating threads, you're only getting one single kernel thread, even though you have, because only one of them is running at a time. The parent and the child. Parent waits for the child, child executes, goes back to the parent, vice versa. Many to one, in terms of the model, we have these are the user threads, and they're inside of one kernel thread. So with this type of mapping, it doesn't really matter. I mean, we can just have many different user level threads inside of one kernel thread. We can make the kernel level thread bigger. It houses many user threads. We can get all those threads being processed from a kernel perspective. Just keep in mind, user level and kernel level have different thread abstractions. And processes run at user level. One-to-one. Each user thread maps to one kernel thread. That's everybody. That's Linux, that's Unix, that's Solaris. Everyone's doing a one-to-one mapping because it's easier. We're not going to lose any threads, and it's just simplified. But there's been a lot of experimentation with the other different models. There's no law that says it has to be one-to-one. Somebody might come out with a better model in the future that does multiple to one. Well, think about it. If we had all multiples and the kernel thread was running, we could split the multiples out over different processors. Single processor unit, one-to-one makes more sense. Multiple processors, multiple CPUs, maybe multiple threaded patterns would make more sense. Because then you can spread the work out among multiple CPUs from a kernel perspective, which means you're going to have more than one kernel thread. Here's a one-to-one model where we have one user thread that's associated with one kernel thread. That's our typical model that we're seeing today. It's easier to understand. A many-to-many model allows many user level threads to be mapped to many different kernel level threads. Maybe for multiple CPUs that makes a lot more sense, because then we can have many different threads running. We want more kernel threads if we have more CPUs, because then we can schedule them off differently. If everybody's inside of one kernel thread, it's only going to run on one processor. So, allows operating system to be create a sufficient number of kernel threads, more kernel threads. Solaris prior to the version 9 Windows NT with a thread fiber package, older versions of Windows were supporting this model. A many-to-many model where we have many user threads that are mapped to many kernel threads. That's going to be fastest model for multiple CPUs. Single CPU doesn't really matter, one-to-one works just fine. So then we have a two-level model, similar to the many, except that it allows the user thread to be bound to a kernel thread. And examples of that are going to be like some of your variations of HP Unix, UX Unix, Solaris is in there too. Some of the earlier versions. Here's our two-level model picture where we have, kernel thread, user thread, and we can basically map them so we know which one's going to which one. So, threading issues. Okay, so we have the semantics of the fork and the exe system calls. Many different varieties of exec. Some people won't use an exec, they'll use a fork. An exec is sort of like a lightweight fork. It actually doesn't create all the same overhead. We have the thread cancellation process, signal handling between the different threads, thread pools, thread-specific data, and scheduler activations. How are we going to schedule all of these threads to run? So let's take a look at the semantics of the fork and the exec. Does fork duplicate only the calling thread or all threads? This is one of the biggest problems in terms of putting multiple threads inside of a process. What are you going to get? If the parent has multiple threads, which one of the parents or which one of the threads are you going to put inside the child? So there's no answer to these questions. These are just problems that come up in terms of the semantics. This is why, this is why most operating system developers have gone one-to-one. The mapping is just ridiculous in terms of its complexity. What about thread cancellation? How are you going to cancel one thread inside of that process, instead of the multiple processes? So terminating a thread before it is finished. Two general approaches here. Asynchronous cancellation terminates the target thread immediately, or deferred cancellation allows the target thread to periodically check if it should be canceled. Signal handling is probably the most difficult to program with. Signals are used in Unix to notify processes. We don't really send too many signals in Windows environment. When you press Control Alternate Delete, it is a signal. Brings up Task Manager. And then when you press on one of the items in the Task Manager, the running programs, and you select to delete, it sends a kill signal to the processes. So it's run through the Windows GUI interface. You actually do have signals. Actually, you can press Control-C, usually, in a DOS prompt to control break something. Control-Pause, C. So you can terminate, you can do very limited things, but you can actually generate signals. So signal handlers use to process the signals, and the signal is generated by particular events that might occur, and it's delivered to a process, and it's overhandled. So options here: deliver the signal to the thread to which the signal applies, deliver it to every thread in the process. How are you going to know which one it's supposed to go for? Which is kind of confusing. And then deliver the signal to certain threads in the process, but not all the threads in the process. And then assign a specific thread, this should say thread, to receive a signal for the process. So signal handling gets complicated as well in terms of the mapping. So it's a one-to-one makes a lot more sense. And then we have thread pools. So create a number of threads in a pool where they all wait for work. So instead of going one-to-one and you're creating a thread, having it do some work, you just have a thread pool out there. Advantages: usually slightly faster to service because you don't have to wait for one to be created, it's already created, using an existing thread. And then allows the number of threads in the application to be bound to a size of a pool. So you can control how many threads are going to be bound to the process. So you can figure out, well, how to better control them, which one you're going to use, which one you're going to kill. And then we have this concept of the thread-specific data. So it allows each thread to have its own copy of data. So each thread has its own data, which means it doesn't necessarily have to share the data. Useful for when you don't want to have, do not have control over the thread creation process, especially when using a thread pool. So scheduler activations, we have this thing called an activation record, or activation records, which are the instructions that are going to be performed by each one of the processes. And these ARs, or activation records, are stored on a stack structure inside of the process space. So remember that little thing that said stack, and on the other side it said heap, and the stack was growing up into the heap, and I went through that last time. Those stacks are holding what's called the activations, or activation records. And so we can schedule the activation records within each one of the processes using the stack that's associated with the process. So with both the many-to-many and the two-level models, it requires communication to be maintained for the appropriate number of kernel threads allocated to the application. So then we have to keep track of which kernel threads are allocated for each one of the activations so it can be scheduled properly. And then it provides upcalls. So you can have an upcall, which is what it's called. It's a communication mechanism from the kernel to the thread library to upcall to see which thread is going to be to run next. And then the communication allows for an application to maintain the correct number of kernel threads as well. So just know that we have the scheduler activations as a concept. We'll see that with activation records and scheduler activations when we looked at CPU scheduling coming up. So pthreads, we keep calling it pthreads, a POSIX standard. So it's the API for creating and synchronizing threads, which is what we're doing when we program with threads. And so the API specifies the behavior of the thread library, implements it using a library API, which is what you're going to use inside of C if you program it in C. So, common in Unix operating systems, Mac OS X. So. Windows XP threads. Well, it implements a one-to-one mapping. So each thread contains a thread ID, a register set, a separate user and kernel stack, and then private data storage area. So if you go into the task manager, you see processes that are running, you see user level and you see kernel level processes in there, usually identified by the user. Each one of them actually has an ID next to it, so you can actually kind of look at that. So we have the register set, the stacks, the private data known as the context of the thread. And then we have the primary data structure itself for the thread, which includes execute thread block, kernel thread block, and thread environment block. So, very limited user control, however the abstraction does exist. Windows definitely has thread libraries associated to it, and it is a one-to-one mapping. So Linux threads refer to them as tasks rather than threads. So we have a task, which is kind of interesting because we have task manager or task scheduler in Windows. So it's kind of using the same terminology. The thread creation is done through the clone system call, and clone allows a child task to share the address space of the parent class or parent processor task. Java threads, kind of interesting. They're managed by the JVM. Actually, every running class is a thread. So instead of every running program, it's every running class. So the classes themselves have inter-process communication, and they share information back and forth, which is kind of interesting. It's all controlled by the security manager. So you can set a security file to give one class access to another class to communicate back and forth. You can put restrictions and things on that. So they can't open and close files. Or one process can, but the other one can't. Different things that you can do with that. So they're created by extending the thread class and implementing runnable interface. So you just use the keyword runnable, and it makes it a thread. So it gives you interface, gives you access to the running class as it's running. So the Java thread states, as we're looking at here, very similar to the thread states of a Unix system. So we are new, then we start, makes us runnable, and then we get blocked, and then we die occasionally. And we're all done, exits. Don't really have to know anything about the Java thread states, just know that there are different states to every thread that runs, because it has to transition between different states. If it doesn't transition, then we end up with serial processing. So, all right, that is your thread concept. And that is actually 4A. A related lecture, 4B, is also on the thread concepts, but it is specifically looking at inter-process communication in terms of the concept. So we'll go for a few more minutes here on inter-process communication. So this is lecture 4B, and then this will bring us up to date actually. So we have this concept of the threads talking to each other. We have deadlock, and then we have the classic IPC problems. So as I previously mentioned in the lecture number 3, this producer-consumer model. So what we're trying to do now is look at how we're going to get multiple threads running together to speed up the processing of our program. So if we're running a program, and the program's going to be called CP or copy, or even rename, and actually rename doesn't really need this, but copy does, because we're going to take data from one thread and copy it into another. Or excuse me, we're going to have two threads. One's going to read and the other one's going to write the data. So in the producer-consumer model, the producer produces, puts into a buffer pieces of information, and then the consumer reads. So it gets from the buffer and consumes the information. And the buffer is shared between the two processes, or the two threads that are running. And I'm going to use the word thread and process simultaneously. Really, they're threads, but I like to use the words process instead of thread, but they're really threads. So the buffer is shared, and usually there's a shared value that goes between them. So we can get two threads to essentially perform the work together. It's like getting two people to work together instead of just one. So you have twice the processing power. Well, in theory, if the threads are getting along. But just like how you can get two people that don't work well together, you can get two threads that don't work well together either. One person is putting stuff together, the other person is undermining, is doing something else. It's conflicting or undoing what the other person is doing. So here's the process in time as we look at it, because it's all about time. Which is why we have two processes working together, because what we want to do is have it finish faster. So we're concerned about how much time it takes. So both processes are started at the same time. Consumer uses some old value. If we have a problem that produces, we can have essentially a producer that's producing and a consumer that's consuming, and depending upon the synchronization of the two, which is why the synchronization is important, we might have an old value in the buffer that's being consumed, that's outdated. Or we might have the buffer corrupted by the producer producing too much and the consumer not taking anything out at the right order. So things might come into the buffer and go out of the buffer out of order. or you might get the wrong value out depending upon when you go in to go look at the value. So if you're putting produces puts 1 in, puts 2 in, puts 3 in, puts 4 in, and right around this point he put 2 in. The buffer here didn't read 1, so we got 3 instead of 2 because 3 was in here before this guy had a chance to look at it. So it's about the synchronization, which is the key to all this. So we have some conditions that come out of this. One of them is the race condition. It's kind of like what two people would actually do if they were working together. One person's assembling, let's say they're building something together. One person could be assembling something, and then the other person could be adding something to it. And then you're always at race with each other to see which one's going to finish their part of it. And depending upon which one finishes, you might not get the right results, depending upon what's going on. So because of the timing and the processes, which process starts first, there's a chance that there's a different execution result that comes out of this. It may end up with different results. So you might have at any one moment of time, half of it finished and the other half not finished, or something. Or different values that come out of it depending upon the race that's going on. It's kind of like how people spend money. You only have so much money, you're going to spend it as fast as you can. Well, some things can get purchased and some things can't, depending upon the order that you're purchasing stuff in. So we have this concept called the critical section. So the critical region or critical section. It's a section of code which processes, access, and modifies. It's the shared variables. It's the buffer. So we call it, this is terminology for you, we call it the critical region, and then we have this thing called mutual exclusion that says one process or thread can't go in and change it if the other person's changing it. Otherwise you're going to overwrite what you did. It's kind of like how people pull up Google Docs and they start editing. 5 people start editing, and then that's the critical region. It's the shared information among everybody. And then the mutual exclusion means only one person can open it up, lock it, and then they can edit it. And then when they have to save the changes before another person can save their changes. It provides for more consistency between the changes, so the document itself could have some more reasonable, reliable results coming out of it. So the critical section is what we're trying to protect. Mutual exclusion is preventing or ensuring that only one specific number of processes are in the critical section at any one moment of time. So only one person can change it. So why processes need to communicate? Well, they need to synchronize their work. If we're going to create multiple threads to run inside of a process, or multiple processes to run simultaneously to accomplish work for a program, they have to communicate with each other. If they don't communicate with each other, it's hard to tell what work is being done and what the final product is going to look like. So to synchronize their executions and also to exchange data and information back and forth between the different processes. That's how come they need to communicate. So rules to form the critical section. No two processes may be simultaneously inside of the critical section, that gives us our definition of mutual exclusion. So if you want to remember, mutual exclusion is that only one process at a time is inside of the critical section. No assumptions are made about the relative process speeds or number of CPUs. And a process outside of the critical section should not block another process. Because if one outside blocks one from coming in, then we have, well, not only do we have arguments going on, but we have work that's not being done. We have busy wait situations that happen. And no process should wait forever before entering a critical section. Otherwise, you get starvation. So if you have this critical region and you're protecting it, the race condition is whoever gets there first is going to get. It's kind of like people, you have open seating in an auditorium, and you open up the door, and people rampage over each other to get to the best seats. And the people who get there first are going to get those best seats. That's a race condition. Or you get people that come in the night before, they sit down in the seat and they never leave. So you get starvation because no one's going to be able to use those seats. Or the guy say, oh, they're going to block off the first 3 rows because it's for handicapped or for wheelchair accessibility or something. That's starvation. Those seats are never going to be used, which is not good. Or busy wait, where a process comes in and says, is the seat open yet? No. Seat open yet? No. See opening it? No, and you're busy standing around waiting for the seat to open up, but you're not doing anything because you're waiting for the seat. So, in terms of the mutual exclusion problem, here's the starvation. By definition, is indefinitely delaying the scheduling of a process in favor of another process. So processes starve each other because they're delaying each other. They're blocking something. If you have a process that's using I/O and it's supposed to be reading a disk, a CD-ROM, and it's supposed to be playing the music players do this all the time. Anybody else wanting to use the CD-ROM, not going to use it. They're going to starve to death. So you tell another program that you want to burn a disk while a disk is running in the same drive, not going to happen. It's going to say waiting, 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 indefinitely. That's caused by starvation. The cause of it usually in a bias in the system scheduling policy, a bad scheduling algorithm, usually a problem. It's kind of like the waiting window, where the window has been sitting out too long, it's been minimized too long, and it'll happen with windows that have been minimized. And the memory manager will actually take it out of memory, so it won't be in memory. Part of it won't be in memory anymore because it'll reuse the memory. And then you click on the window, it says waiting. It will actually come back to life, but maybe never. It's in the starvation mode because it doesn't have any resources associated with it. No memory has been assigned to it, or the memory that was assigned to it was taken away. So another solution here is to implement some form of aging. So if the process has been waiting long enough, then it gets a chance. Otherwise, it's not going to get a chance. So another problem that occurs is called deadlocks. And a deadlock is when two or more processes are blocked waiting for an event to occur that never occurs. So processes are waiting for something to happen and that never happens. So they're deadlocked. It's kind of like how you have a one-way bridge and two cars enter from both sides and neither one of them wants to move because they want to both cross the bridge, but they can't both cross the bridge together. So there's traffic deadlocks constantly. So generally, A waits for B to do something and B is waiting for A. That's actually referred to as a circular wait as well, and circular waits cause deadlocks because A is waiting for B, which might be waiting for C, which is waiting for A, which is waiting for B, which is waiting for C. So nothing's happening. They're all waiting for each other. Both are not doing anything, so both events never occur because nothing's going to happen. They're both waiting. So how to implement mutual exclusion. 3 possible ways of doing it. And these have all been experimented throughout time. Application level. Programmer builds some method inside of the program, and the method produces the mutual exclusion. Hardware level. So we have specific hardware instructions provided to implement the mutual exclusion. Depends on the computer system you have. So can Windows do a hardware level mutual exclusion? No. No guarantee what hardware we're looking at. Unless you build a system that has special hardware, then every system that operating system runs on has that hardware instruction. Not going to work. Or operating system, which is how they're doing it, provides some services that can be used by the programmer. So, or application level. So, all schemes rely on some code for enter the critical section, exit the critical section. So the Windows operating system will actually perform the mutual exclusion operation, but the user doesn't have any control over it. So will Linux actually, performed at an operating system level. May also be performed at an application level depending upon what type of application development you're doing. So application mutual exclusion. The application itself is implemented by the programmer. So the programmer has to know what they're doing in terms of the mutual exclusion. Hard to get correct and very inefficient. If every application you built had to do mutual exclusion on critical sections, so to protect data, to protect memory, it's going to be too time consuming for the programmer, and it's going to be extremely inefficient. They all rely on some form of busy waiting to process, to test a condition, set a flag, loop around, test the condition again, see if it's still there, loop around. So it's not very efficient. Example of putting one together from a programmer perspective. We're looking at a producer and a consumer model here, where the producer is going to produce something and then lock something, put it into a buffer, and then set a lock to 0. This is sort of like a mutex, actually, but it's done by the programmer itself. So we have a producer and a consumer. And then the hardware mutual exclusion, we have a test and a set instruction that's set. So perform a test. We're basically setting an on or an off on a hardware device to perform the mutual exclusion. So if one process is using it, it's going to go check, and then it's going to set it when it's done using it, and then another process can go in and use it. So it doesn't have to do that busy waiting to go check for a value. The test from a hardware perspective can automatically signal the other process, hey, okay, wake up, we can use you now, kind of thing, which is faster. So hardware level is always going to be faster, actually. So in order to exchange the instruction, you can swap the values back and forth, kind of like a variable, but we're not keeping it in memory, we're keeping it from a hardware on or off perspective. Advantages can be used in single or multiple processors with shared memory. Simple, therefore easy to verify. Can support multiple critical sections. Disadvantages is we have that busy waiting that's being used. The process is going to wait till it gets signaled that it can run again. Starvation is possible if something is hung up. And then deadlock is also possible, especially with priorities. So deadlock is also an issue. So. Disabling interrupts is another form that can also be used for hardware mutual exclusion. So on a single CPU, only one process is executed, and then concurrently achieving the interleaving execution by using interrupts. So done with interrupts. So you can disable the interrupts when you're sure that only one process will ever execute and you don't have multiple processes. They're going to fight for the resource. So one process can lock the system or degrade the performance greatly if you have things turned off. So mutual exclusion through the operating system. This is where people get most of the programming experience from in terms of semaphore and message passing. And I'm going to wait until next week to do this one, because now we're starting a separate section. So someone remind me that we stopped on slide number 17 of lecture 4B. And I won't do as much review next week. I think, if I had started in at the beginning, some people were half asleep through the last week's lecture, which was the first class after not being around for a while. So next week we will start with mutual exclusion through operating system and look at operating system concepts of semaphores and message passing. And that is all for this week. So I will see you next Monday, unless I'll see you in the next class.